In a universe of infinite possibilities, we dive into the most profound questions of our existence. Join us as we explore parallel universes, time travel paradoxes, and the mysteries of cosmic evolution with distinguished physicists and philosophers from around the world. Today, we're privileged to welcome Professor Vladimir Liponov, who challenges our conventional understanding of space-time and contemplates the implications of Fermi's paradox across multiple dimensions. Are we alone in this vast cosmos, or merely isolated in our three-dimensional perception? Could advanced civilizations exist beyond our dimensional reach? And what does quantum gravity reveal about the nature of our reality? From black holes to wormholes, from Einstein to Hawking, we're about to embark on a mind-bending journey that will forever change how you perceive the universe around you. Prepare to expand your consciousness as we delve into the quantum realm where science meets philosophy on Quantum Dialectica. Dear viewers, welcome to the third episode of the Quantum Dialectica podcast. I'm delighted to host our guest today, Professor Vladimir Liponov, member of the International Astronomical Union and the European Astronomical Society. Professor, welcome to our show.
Hello, and welcome to all the viewers.
Welcome. Could you please explain why scientists believe that the possibility of time travel and even travel between different universes is connected to black holes? Why do they hypothesize that these black holes might be gateways to other dimensions of time and space?
That's an excellent question. I sometimes wonder why my colleagues think this way. All of us, my colleagues and I, study fundamental subjects in our fields daily, working to develop and advance them. But inevitably, we all encounter this fundamental question: what existed in the universe immediately after its formation? Astrophysicists have reached one conclusion: there was a state of extremely dense matter. We are now certain that the density of the universe during the first nanoseconds of its formation was enormous. This naturally leads cosmologists to the next question: where did this state come from?
Exactly. That's the crux of the matter. Where did this density come from?
Listen carefully to what I'm about to say, and we'll find the answer. Let's think deeply like natural philosophers and scientists and ask ourselves, where in nature can we find states of extraordinary density? What's your answer to this question?
Honestly, I don't know.
But physicists do know. There's the theory by Roger Penrose, or more accurately, the Penrose-Hawking theory. According to this theory, it's possible that the gravitational singularities found in black holes formed during the gravitational collapse of large dying stars in our universe. These states of tremendous density exist below the event horizon of black holes and are therefore hidden from us. From these gravitational singularities, it's possible that a universe like ours could form. When working on this theory, Penrose and Hawking proposed that in the center of a black hole, a state of extreme density and temperature inevitably appears. They wrote about this since the 1960s. Thus, we understand that states of extreme density can also exist in our time and space, and familiar matter may emerge from this state. In the Big Bang theory, the universe begins evolving from a state of extreme density to the present time. Now we can hypothesize that other states of extreme density may appear in the universe, though we cannot observe what happens inside black holes. New black holes are continuously forming. Astronomers using robotic telescopes observe this happening approximately once a week, known as gamma-ray bursts. Now, as a natural philosopher, you're fully aware that the universe emerged from a state of extreme density, and within it, states of extreme density were born. These are black holes. If you ask what caused this extreme density state, the answer is simple: from a black hole, presumably from another universe where a black hole formed.
So it's possible that our universe appeared
inside a black hole of another universe.
And therefore, we can assume there are many universes.
Yes, many scientists support this idea, but I'd like to complete my thought.
But we can't observe them because they're inside other black holes.
Yes, exactly.
And we can't cross the event horizon.
Correct. We've now established that it's possible a universe formed from a black hole, or rather, emerged from it. What we know now is limited to the fact that beyond the event horizon, beyond the point of no return, we forever lose information about any object that falls into a black hole. According to general relativity, when an object enters the spherical collapse of a black hole, it disappears with no return. But we don't know what happens in that region of the black hole where density is tremendously high. We do know, however, that it's possible that inside the black hole, quantum gravity theory might be at work, a theory no one has yet discovered in our spacetime. Therefore, we can only speak about this hypothetically. But how, for example, can we imagine a massive black hole? Such black holes actually exist in reality, a type of galaxy that exceeds the sun's mass by billions of times. Spacetime in such a black hole has no boundaries, allowing any object the possibility to move in any direction, to any place to the future or past, along world lines that pass through the singularity. After that, these lines could close in other universes and in different locations. This idea was first proposed by Albert Einstein and Nathan Rosen, making it seem as if different locations are connected through wormholes, spacetime tunnels. Many scientists write about this in the Physical Review journal.
Perhaps this idea seems more realistic than time travel, meaning that traveling between universes appears more realistic than traveling through time within a single universe.
Yes, but it's unknown what that universe would be like. If we assume that objects in other material states exist there, that universe would have its own many-bodied fields in a four-dimensional space. If another universe existed beyond the event horizon of a black hole, it would be like our universe evolving with all the diversity of life within it. But then Fermi's paradox emerges again, along with a question, could they develop to reach us?
It might also be difficult for them to cross the event horizon. Yes, there's a lot to consider.
The horizon problem remains present. Once physical time extends through the singularity into another universe, a wormhole appears. Within some time, we could return to our universe, but in a different place, on the other side of the metagalaxy. This is essentially instantaneous travel through a wormhole. If we went back further, billions, 100 billion light years from the point where we were before, this would be a journey through space-time. But all of this is theoretical for now, within the framework of theory, because we currently don't know how to achieve this. Once, we at the Institute of Astronomy who were studying Fermi's paradox met with astrophysicist Nikolai Kardashev, who was working on questions about extraterrestrial civilizations. When many Earth-like planets were discovered, he told us, "Colleagues, something isn't right. There are many planets similar to Earth, but where are the civilizations? I thought we weren't receiving signals from them simply because they weren't numerous and had no place to develop, but it turns out they exist, yet there are no civilizations." That's what Kardashev said. Many now explain the absence of signals from extraterrestrial civilizations by suggesting they don't last long. I see this as one possibility. Another possibility is that we are the creation of a higher intelligence or civilizations millions of years more advanced than ours.
And there might be civilizations from other universes, millions of years more advanced, not even in the same material state as us. We might be a laboratory for them.
Is there evidence that such civilizations are capable of something amazing and extraordinary? It's not certain, and this doesn't require billions of years of evolution. I once calculated how many years we would need at the current pace of progress until we could create artificial universes in physics laboratories, preferably in a location far from us. I concluded that we would need 5,000 or 6,000 years at the same pace of progress. But let's return to black holes. During the meeting with Kardashev, I asked him, "You see the possibility of civilizations of three types. The first uses the energy of its planet, the second maximally uses the energy of its star, and the third uses the energy of the galaxy. Why don't we hear anything about these type 3 civilizations?" He answered, "They left and went to other universes through black holes and wormholes." What Kardashev said seems to me a plausible possibility, but it's not natural. Physicist Andrei Linde believes that the existence of many universes is possible, but they remain unknown to us. We only know our universe. This is probable from a physics perspective. It's also possible that the concept of time will collapse in real physical theory. By the way, there's something very important. Hawking, in his works, tried to connect the concepts of free will and time. The problem with this connection emerges when we go back in studying the history of the universe to the singularity state, where the direction of time is lost. We live in a world with the concept of responsibility stemming from cause and effect, and time always moves from past to future with no return. If the direction of time is lost, there's no place for something called responsibility and causality. Everything is predetermined, meaning there's no concept of good and evil.
So the concept of causality appeared simultaneously with the emergence of time and space?
Yes, with time's direction from past to future.
And the beginning of time is the singularity state?
The singularity state has no explanation, close to those states of extreme density that can appear in black holes.
Can we say then that time and space don't exist in a state of infinite density, as in the singularity?
If you're talking about physical space-time,
The physical, of course.
As quantities we know how to measure, then know they don't exist, because in the state of extreme density, we don't know how to measure them.
It's something beyond human comprehension.
But we don't have the algorithm to measure time or space in that realm we inhabit. With respect to small mass, extremely dense black holes, the concept of the event horizon collapses. But if the radius of the black hole is less than the Compton wavelength, no one can say where this black hole is, let alone where its event horizon is. Since this is unknown, it's possible to hypothesize the existence of particles in this place, tachyons, that move faster than the speed of light. Stephen Hawking touched on this aspect.
He said that scientists succeeded in accelerating particles to 99.99% of the speed of light, but not beyond that. After that, increasing energy no longer led to increased speed.
That's correct. Nothing more was possible. Tachyons cannot be accelerated even to the level of light speed, but particles like photons exist in our universe. Here the question arises, why aren't there tachyons that, like photons, can move faster than the speed of light?
Could you briefly explain this issue, please? Some people don't understand why time would move backwards if we moved faster than the speed of light. Why indeed?
Yes, because all objects naturally move at speeds less than the speed of light. As relativity theory states, exceeding the speed of light leads to the following. Let's assume at point A an event occurred. For example, an explosion. Subsequently, at point B, someone perished due to the shock wave resulting from that explosion. This means the event at A caused what happened at B. We can choose different reference frames or travel through space in various vessels, but in our natural universe, everything moves slower than light. Time flows consistently everywhere, and cause and effect cannot be reversed. However, relativity as a mathematical theory acknowledges the theoretical existence of tachyons. When the theory states that velocity is always less than c, the speed of light, it means the theory doesn't want to violate the principle of causality. But if we remove the causality principle from thermodynamics, for instance, it would become easier to theorize the existence of black holes that could transport objects from the future to the past. Strangely, we don't observe this happening, something that should concern physicists developing these theories. Yet scientists generally don't dwell on this. They consider Fermi's paradox as merely an anecdote told by scientists at Los Alamos. Regarding wormholes, passages between hypothetical universes described by the Einstein-Rosen bridge theory, specific conditions must be met. There must be some form of matter that prevents the passage from collapsing, which would need to be matter with negative energy, called exotic matter. Some physicists believe this is possible, while others don't.
And this matter supports this passage?
This matter somehow counteracts gravity and supports this passage in a remarkable way. This isn't even the dark energy currently expanding our universe at an accelerating rate.
Can we conclude that advanced civilizations, if they exist, might be capable of sustaining such passages and creating exotic matter?
Why not?
Of course, they would need to be significantly more advanced than us.
If I were a natural philosopher who relies on tangible evidence, we must eliminate human-centrism. We should always recognize that the universe is homogeneous and symmetrical, that Earth isn't special among billions of stars, and that our sun is a very ordinary star among billions upon billions of similar stars. Everyone knows there are billions and billions of stars like our sun, as well as billions and billions of galaxies like our Milky Way. Believing we're the only civilization is foolish from the perspective of natural philosophy and physics. It's simply absurd to think that way. This is why Fermi's paradox doesn't just concern why alien spacecraft aren't landing from neighboring stars, but rather why no one from the future comes to visit us. In light of the hypotheses currently being resolved through theoretical quantum gravity, Fermi's paradox specifically collides with the time paradox. Yet no one comes to us from the future. Here we can't just respond that these civilizations don't want to communicate. Let's consider this carefully. Among the millions of civilizations that could hypothetically have emerged and existed in the universe for a relatively long time, at least one would likely have invented a time machine. It only takes 5,000 years to reach and surpass our level of development and learn to harness the energy of an entire galaxy. Nothing would prevent such a hypothetical civilization from discovering wormholes, creating exotic matter and traveling through time, but this is merely a hypothesis. Nothing of the sort actually exists. As long as there are no extraterrestrial beings coming from the future, the time machine also doesn't exist.
But this is in our space-time.
In quantum mechanics, a time machine is possible. There's a concept of reversible time, but in the real world around us, nowhere does this reversible time exist. However, this type of time does exist in theoretical physics.
But It's possible there exists a four-dimensional space.
Yes, yes.
So if there's a civilization existing in three-dimensional space, it might never notice the existence of other civilizations in four-dimensional space.
This is another scenario for our universe's origin. There are currently two scenarios, one that's become somewhat outdated, the steady inflation universe scenario, and the other is the inflationary universe scenario, primarily developed by Moscow State University graduates Andrei Linde and Alexei Starobinsky. Before them, researchers at the Physics Institute in St. Petersburg were working on similar scenarios. The steady-state universe model was previously developed by a single person a long time ago. I don't recall which year exactly. The famous astrophysicist Fred Hoyle, former director of the Cambridge Institute of Astronomy, who created the steady-state universe model in 1948. However, this model lost its significance after the discovery of cosmic microwave background radiation. What is the essence of Andrei Linde's inflationary theory? Linde believes that new universes are constantly being born and emerging as a result of quantum fluctuations.
In a hypothetical four-dimensional space,
we have three fixed dimensions plus time, and this is exactly our concept of space-time. In Linde's model, the universe gives birth to universes, and this process never stops. It's exponential. This process appears deceptively problematic because it remains consistent throughout time. If we move according to it, we find it has a distinctive time that isn't tied to the exponential point where we exist. Therefore, the exponential is constant and describes processes well, and it's eternal. But from what perspective? Eternity is a concept of psychological time. I thought about this. How can we reconcile this constancy with inflationary processes? And what about the singularity state that has the concept of physical time? Perhaps we can speak not about time, but about the number of attempts made for universes to be born. In Andrei Linde's scenario, universes never stop reproducing, and we don't know how to evaluate that in terms of the concept of time. Which time should we take as a starting point?
So we can say that different space-time levels are continuously being generated?
Yes, and in each of these levels, people believe the world is localized. That's how we think. We live in one enormous universe, but this isn't definitively known yet. Perhaps somewhere there's a passage through a black hole singularity to cross into another universe. Perhaps someday humans. All this is under discussion and active research among physicists. The same applies to the theory of continuously reproducing universes. This also relates to whether we can or cannot use the concept of physical time when describing processes inside a black hole. We don't know how to define it or determine an algorithm to measure it. Perhaps someday humans will abandon this concept. In quantum mechanics, there are quantities that can't be measured, for example, the wave function that no one has ever seen. There was hope that quantum mechanics specifically would explain the concept of the arrow of time, from past to future, so it could be applied to thermodynamics as well. I want to say that Hawking proposed an original interpretation of science fiction stories involving parallel worlds, which is practically a generalization of Feynman's theory. He suggested the following. Imagine we observe a physical body moving from point A to point B along a straight line. What did Feynman propose? He suggested we imagine that the body can actually move along different curves, meaning any path is possible when the body transitions from A to B. We see that under these conditions, the most probable passage of the body occurs along a specific line. But no one has denied the possibility of other probabilities. Hawking applied this possibility to the entire universe, that the universe moves from A to B in space-time. It was small, then expanded, and once again will become small. That's what he said. I believe the universe will become small again, but I don't think it will happen this way. But what does it mean when I say, I don't believe? No one knows whether it will be like that or not. I know there's no person who can disprove or prove it. But my opinion might not matter to anyone, and I know precisely that, generally, there's no person who can know the exact answer to the following question: what will happen to the universe later? Hawking, for example, assumed that from A to B the universe expands and afterward will contract. This assumption has now changed because new data doesn't indicate the universe will stop expanding. And there's Richard Feynman, who created the one-electron universe theory, where all electrons are actually one electron appearing alternately at different points in space. Perhaps billions of parallel universes really do exist. One evolved according to a law from A to B and another evolved differently, but they evolved in parallel. Feynman suggested that humans, in this case, could return to the past, but it would be a past in a parallel universe where anything could be done, and the future wouldn't change. All this remains an unprovable hypothesis.
So we can explain Fermi's paradox. We apply Fermi's paradox to three-dimensional space, not four-dimensional space. And that's all there is to it.
Each of these levels, people believe the world is localized. That's how we think. We live in one enormous universe, but this isn't definitively known yet. Perhaps somewhere there's a passage through a black hole's singularity to cross into another universe. All this is under discussion and active research among physicists. The same applies to the theory of continuously reproducing universes. This also relates to whether we can or cannot use the concept of physical time when describing processes inside a black hole. We don't know how to define it or determine an algorithm to measure it. Perhaps someday humans will abandon this concept. In quantum mechanics, there are quantities that can't be measured, for example, the wave function that no one has ever seen. Hope that quantum mechanics specifically would explain the concept of the arrow of time from past to future, so it could be applied to thermodynamics as well. I want to say that Hawking proposed an original interpretation of science fiction stories involving parallel worlds, which is practically a generalization of Feynman's theory. He suggested the following. Imagine we observe a physical body moving from point A to point B along a straight line. What did Feynman propose? He suggested we imagine that the body can actually move along different curves, meaning any path is possible when the body transitions from A to B. We see that under these conditions, the most probable passage of the body occurs along a specific line, but no one has denied the possibility of other probabilities. Hawking applied this possibility to the entire universe, that the universe moves from A to B in space-time. It was small, then expanded, and once again will become small. That's what he said. The universe will become small again, but I don't think it will happen this way. But what does it mean when I say I don't believe? No one knows whether it will be like that or not. I know there's no person who can disprove or prove it, but my opinion might not matter to anyone. And I know precisely that generally there's no person who can know the exact answer to the following question: what will happen to the universe later? Hawking, for example, assumed that from A to B the universe expands and afterward will contract. This assumption has now changed because new data doesn't indicate the universe will stop expanding. And there's Richard Feynman, who created the one-electron universe theory, where all electrons are actually one electron appearing alternately at different points in space. Perhaps billions of parallel universes really do exist. One evolved according to a law from A to B, and another evolved differently, but they evolved in parallel. Feynman suggested that humans in this case could return to the past, but it would be a past in a parallel universe where anything could be done, and the future wouldn't change. All this remains an unprovable hypothesis.
So we can explain Fermi's paradox. We apply Fermi's paradox to three-dimensional space, not four-dimensional space, and that's all there is to it.
Yes, but only if all development paths of universes are unconnected with each other, which is the case in the modern interpretation of quantum gravity theory, and this theory is workable. Richard Feynman illustrated in his diagrams the possible probabilities for the birth of particles that were later discovered and named Higgs bosons. The scientists who worked on creating the Hadron Collider knew what they were looking for and understood under what conditions and where they could detect these particles because they were estimates from the standard model of a single universe. But when discussing different parallel universes, scientists must also study different linear universes within the framework of quantum gravity theory.
But this gravity hasn't been discovered yet.
Yes, it exists, of course. Various models can be created in theory, but I think they will eventually collide with some modified version of Fermi's paradox. As soon as we assume the existence of an infinite number of universes, things become more complicated. We would be forced to assume the existence of life in many parallel universes, which means billions upon billions of places where at least one advanced civilization may have emerged. And we return to Fermi's paradox.
So we are definitely in a closed system?
No, we can't say that with certainty. We can't give just one unambiguous answer. Some believe that civilizations have short lifespans and don't exist long enough to encounter one another. In our recent conversation, I used the analogy of a Christmas tree with strings of twinkling lights that illuminate one after another. That's how civilizations might be, but this is just a concept. As Enrico Fermi said, I created this impression to make the issue more understandable, but we still don't know who created this metaphorical string of lights, according to what blueprint its small bulbs light up and extinguish, and why they shine for only a brief moment. We don't know. And that's why humanity must be prepared. Stephen Hawking frankly stated that Earth's inhabitants should colonize the solar system because We could easily experience what happened to the dinosaurs. A meteor could strike and we'd all become extinct. Even if that's unlikely, we might destroy ourselves with our nuclear, chemical, and biological weapons. However, I remain optimistic. There's always a way out. Let's assume we live in a rational universe created by someone. The unsolved Fermi Paradox can be understood as a sign to find reasons for optimism.
To think about how everything began.
Yes, and to always realize that good and evil won't disappear, and sooner or later there will be consequences.
Well, let's end on this optimistic note.
Although physics questions this.
Of course, our discussion today was somewhat challenging. I'll recommend all viewers read Stephen Hawking's book. By reading Hawking's book, readers can envision what we discussed in this interview. Thank you very much once again, and goodbye until new episode.
Thank you.
Thank you, dear viewers. With this, we've reached the end of our conversation for today. In this episode, we spoke with Professor Vladimir Liponov. Join us next month for new episodes of the Quantum Dialectica podcast. Don't forget that this podcast is available on all listening platforms. Thanks for watching.